Hey everyone and welcome. We're about to dive into the invisible forces that pretty much run our entire world, the magnetic effects of electric current. Now this is Chapter 12 from your Class 10 NCERT science textbook, and let me tell you, it is absolutely essential for your board exams. So let's get into it and break it all down.
So here's the plan. We're going to walk through this entire chapter, piece by piece, to make sure every single concept is crystal clear. By the time we're done, you're going to feel super confident about everything you need to know for your exams.
And here's our roadmap. We'll start with the accidental discovery that kicked this whole thing off. Then we'll figure out how to actually see and shape these magnetic fields. After that, we'll look at the real physical force they can create, see how it all works in our own homes, and then finish up with a super quick recap. So first stop, the very beginning.
So let's rewind the clock and talk about the spark, literally, that started this whole field of study. I mean, how did anyone even figure out that electricity and magnetism were connected? Well, turns out it was a total accident.
Picture this, it's 1820, and a physicist named Hans Christian Ørsted is in the middle of a lecture. He's got an electric circuit set up, and he just happens to notice that every time he turns it on, a compass sitting nearby goes a little haywire, the needle twitches. That tiny, simple observation was a complete game changer. It was the first solid proof that electricity creates magnetism, and it laid the groundwork for things we can't live without today, like radio, TV, you name it.
Okay, so we know there's a connection, but what does this magnetic effect actually look like? You can't see it with your eyes, right? It's an invisible field of force. But we've got some pretty clever ways to map it out. Let's see how that works. First things first, a key definition you have to know. A magnetic field is just the area around a magnet where you can feel its force. You can kind of think of it like the magnet's own personal bubble, or its invisible aura of influence. And the cool thing is, you can actually trace these invisible fields yourself. It's a classic experiment. All you need is a little compass, you just place it near the magnet, mark where the needle points, then you slide the compass down and mark the new spot over and over. When you connect the dots, you are literally drawing the invisible lines of force.
And when you do that, you end up with a map that looks something like this. And these lines have very specific rules they always follow. They always form closed loops, shooting out of the North Pole and circling back into the South Pole. Oh, and inside the magnet, they go from south to north. And see how they're all bunched up at the ends? That's where the magnetic field is the strongest.
This brings us to a question that loves to pop up on exams. Based on what we just talked about, using a compass to trace the field, take a second and think about it. Why can these magnetic field lines never, ever cross each other?
And the answer is just simple logic. Remember, at any single point in space, a compass needle can only point in one direction. If two field lines crossed, that would mean that at that exact point of intersection, the magnetic force is pointing in two directions at the same time, and that's just physically impossible.
Okay, so we've got it. A current creates a magnetic field. The next logical question is, can we mess with it? Can we control the shape and the strength of that field? And the answer is a huge yes. And it's how we build all sorts of incredibly useful stuff.
It turns out, the shape of the wire carrying the current is everything. If you have a straight wire, like on the left, it creates a magnetic field of simple circles around it. But if you take that same wire and bend it into a loop, like on the right, look what happens. All those field lines get squished together and concentrated inside the loop, creating a way stronger, much more uniform field right in the middle.
So, how do we know which way those circles are going, clockwise or counterclockwise? For that, we've got a super handy trick, the right-hand thumb rule. Seriously, try this with me now. Pretend you're grabbing the wire with your right hand. Point your thumb in the same direction the current is flowing. The direction that your fingers naturally curl, that's the direction of the magnetic field. Simple as that.
Now what if we take that one circular loop and then add another, and another, and another, stacking them all together? Well, then you get this thing, a solenoid. The easiest way to think of it is just like a slinky, but made of copper wire. And this simple shape is unbelievably useful. And here is where it gets really, really cool. When you run an electric current through that solenoid, it acts exactly like a normal bar magnet. You get a really strong, really uniform magnetic field inside, and it has a clear north and a clear south pole. But here's the best part. It's an electromagnet. We can turn its magnetic power on and off just by flipping a switch.
Okay, so we've used electricity to create a magnetic field. But so what? What's the point? Well, this is where things get really fun.
That magnetic field we just created can now exert a real physical push or pull on things. It can create a genuine force.
Now, to figure out which way that push or pull is going, we need another essential hand rule. This time, it's Fleming's left-hand rule. Okay, I want you to do this with me. Get your left hand out. Point your forefinger straight out. That's for the F, field. Now point your middle finger out to the side, making an L shape. That's for the C, current. Now look at your thumb. It's pointing up, showing you the direction of the force or the motion. Field, current, force. Got it?
Let's try it out with a typical problem. We've got an electron that's moving up into a magnetic field that's pointing to the right. So what direction is the force? Now before you jump in, remember the one big trick they always use to catch you. The rule uses conventional current, which flows in the opposite direction to an electron.
So if our electron is moving up, that means the conventional current is flowing down. Okay, get your left hand ready. Point your middle finger, current, down. Point your forefinger, field, to the right. Now, which way is your thumb pointing? It should be pointing straight into the page or into your screen. That's the direction of the force. You've got to practice this one a few times to get the hang of it.
All right, let's bring all this theory back home. Literally, how do these principles of electricity and magnetism actually apply to the wiring in our houses to keep us safe? This is a super practical topic and a very common one for exams.
First up is something you just need to memorize, both for safety and for your tests, the color code for wires. It's a universal standard. The red wire is the live wire. That's the one with the high voltage. The black wire is neutral, which completes the circuit. And the green one is the earth wire, which is a super important safety feature. And that brings us to the two main bodyguards of your home's electrical system. First, you have the fuse. Think of it like a self-sacrificing hero. It's a special little piece of wire designed to literally melt and break the circuit if the current gets dangerously high. Then you have the earth wire. If there's ever a fault and electricity leaks to the metal casing of an appliance, the earth wire gives that current a safe, easy path to go straight into the ground, instead of going through you. Phew! All right, we have covered a lot of ground. So before we wrap this up, let's do a quick rapid-fire recap of the absolute must-know facts for your exam.
Okay, let's nail these down. Number 1, electric current makes a magnetic field. 2, we draw this field with lines that loop from north to south. 3, the right-hand thumb rule tells you the field's direction. 4, Fleming's left-hand rule tells you the force's direction. 5, a solenoid is basically an on-off electromagnet. And 6, fuses and earthing are what keep you safe at home. Got all that?
And I want to leave you with one final thought to chew on. We've spent this whole time talking about how electricity can create a magnetic field that then causes motion. But what about the other way around? Could you take a magnet, move it, and create electricity out of thin air? Well, that incredible idea is called electromagnetic induction, and it just so happens to be the